right, so let's look at an application, maybe not one of the classical application of the Riemann mapping theorem, but an application. This is it seemingly has nothing to do with simply connected domains, and actually in the end the proof is not really that much easier than the traditional proof of this of the lemma that we're going to prove, but it's about as difficult. But it's kind of, I find it kind of an interesting way of thinking about it. The thing is, it's going to be a little tricky to handle the technicalities, but the intuitive idea is actually fairly simple. So what are we trying to prove? We're trying to prove that if we have an open set in the complex plane, and we have a compact subset K in this open set U, then there exists a cycle gamma which is in the complement of K but in U, right? Such that its gamma goes around exactly once around every point of K, and it is homologous to 0 in U. So it doesn't go around anything in the complement of U, right? Now, the way that we're gonna work this is basically the idea is the following. So suppose that K is connected. We'll deal with the, K need not be connected, right? Could even have infinitely many components, but suppose for a moment it was connected. And what we could do is we could take an inversion and take a point of K to infinity, right? Now, what we know is that the complement of a connected set in the Riemann sphere is simply connected, right? So we'll get, and again, this is another sort of technicality we'd need to handle. Well, maybe the complement of K is multiple, components, but suppose it has just one component, then the complement of K, well, the complement of K after the inversion, right, would be a simply connected domain. We could make it a disk. Now, the complement of U, or what corresponds to the complement of U, is now would be a compact subset of this disk, and we could go around it. We'll go around it in the opposite direction. Instead of counterclockwise, we'll go around clockwise, because we sort of don't want to go around the complement of K. We want to go around K, but is after the inversion that will actually that way we'll go around K and not the complement, right? Because we sort of swap. In some sense, we're almost like swapping K for the complement of U, right? So that's the idea. Now, the proof is a bit more complicated because, well, there's all these small technicalities, but try to see the, try to not lose the forest for the trees. And there's sort of maybe more trees here than than in some of the other theorems that we proved. But the idea is actually fairly simple. Okay, so first, this technicality, K could have infinitely many components. Well, but we don't really have to go around K. We could go around something slightly larger, right? And so if we can make K slightly larger so that it still has so that the new K has finitely many components, then we could assume at least it has finitely many components. How do we do this? Well, it's a compact set. We can cover it by, there's a finite cover by open set, so we could cover it by little balls, and then we can actually cover it by slightly smaller balls we can cover it by balls that are such that the closed or disks, actually, we're in complex plane. We're covering it by disks that are inside U, right? And we can make sure that the open disks cover K, right? So the closed disks cover K, and it's a finite union of compact sets compact. So we make this set K prime as a union of these finitely many disks. It's still a subset of U, right? And K is contained in it, right? And it's compact, right? Now, because K is a finite union of disks, it has finitely many components, right? Because each of those disks is connected, right? So maybe some of them overlap, so it might even have one component, right? But it has finitely many components. Now, if we find a gamma that goes around K prime, then it goes around K, and we're done, right? So we can just basically replace K with K prime and have finitely many components. Now, so what about if we have finitely many components? Well, we could take one of them. Let's say K1. We can take them in sequence. K1, K2, K3. But let's take one. Let's say it's K1. Then the union of the rest is closed, right? Because we have finitely many, right? This wouldn't work if you had infinitely many components. But once you have finitely many, if you take one and take the union of the rest, those are still closed sets, right? So if you and K1 is compact, right? So you could try to prove, if you can prove the lemma for K1, which is connected, and for a different U, really, we take a U that is U minus the other components of K, or K prime, right? And if we find a cycle, let's call it gamma 1, that goes around K1, doesn't go around anything in the complement of U, and also the K2 through Kn, right? That's where we're replacing K by K1 and U by this thing, right? So if we can find a gamma 1 that does that, we're done. Why are we done? Because we can repeat the same procedure for each K sub j, and just add these up as this is in the chain arithmetic, right? And we get this cycle gamma that does the trick, right? Because if gamma j is 1 whenever z is in kj, but it's 0. The binding number, or gamma j around z, is 1 for all z around in kj, and it's 0 whenever z is in one of the other k sub, let's say k sub l, where l is not equal to j. And it's still these still do not go around anything in the complement of U. None of them do. So this gamma would work, right? So basically, we can assume, without loss of generality, that K is connected, right? We have a connected K, and we'll assume actually that it's a union, a finite union of disks, as closed disk is, to make some of the other topology easy, right? So that's the first simplification, right? Now we can assume that 0 is in K. Why? Well, because we could just translate things. And we can also assume that K has more than one point. if k is equal to 1 point, then we're done trivially. We can just take a little circle around that 1 point. So we can assume there is more than 1 point. Now let phi, we have to give this a name because otherwise it would be sort of tricky to talk about. So basically just 1 over z, right? So phi is this inversion. It's an LFT, so we're thinking of it as defined both at 0 and infinity, right? It takes 0 to infinity and infinity to 0, and it's so it's this inversion around the unit circle. All right, so that's phi, and that's basically what we're gonna now do to everything. We're gonna take phi of everything. So we're taking 0 to infinity. So if we look at the Riemann sphere minus k, right, and we apply the inversion, give that a name. Let's call that v, right? So it's really the complement of k after the inversion, right? That's v. Now, infinity is not in v, right? Well, because 0 was in k, right? And so in the 0 is not in the complement of k, and v is the complement of k after the inversion. So it's infinity is not in v. 0, on the other hand, is in v because infinity was not in k, right? K was a compact set in C, right? V is not the entire complex plane, well, because k had more than 1 point, right? And we get that, well, k is connected, therefore the image under the inversion is connected, and that's the complement of v, right? I mean, phi is it's a one-to-one biholomorphic map of the Riemann sphere to itself, right? Now, this means that the components of v are simply connected. This is, I guess, a bit of an exercise. It's not hard. Basically, you want to show that the complement of any component of v is connected, right? The complement in the Riemann sphere. If v had only one component, then we're done, right? So the point is, if there are more components, basically, you have this k, and so it's k has a sort of or maybe looking at phi of k, it's a couple of holes, right? And if I fill in one of those holes, it's still connected, right? So that's basically the exercise. Okay. So that means so we can assume that the components of V are actually simply connected. We know that they're simply connected. We can assume that they're finitely many. So we're assuming that there's only finitely many components. Why? Well, we've said that we can assume K was just union of disks. So that's clear then, right? If it was union of disks, then it's clear that the complement is has finitely many components. So let's call them V1 through Vm, right? And now, well, we know that they're all simply connected. So by the Riemann mapping theorem, that's what I mean by RMT. There is just a biholomorphic. This is a typo. This shouldn't be here, obviously. So there's a biholomorphic map. Not two biholomorphic maps, just one biholomorphic. Biholomorphic map from Vj to a disk. So we really are picking finitely many points Q1 through Qm, right? And some disks, and let's suppose that they're all of radius 1. And let's make all these disks disjoint. Basically, stick m disjoint unit disks in the plane somewhere so that they don't touch each other, right? And we have a biholomorphic map from each Vj to the jth disk. And let's say let's call D the union of these disks, right? It's this, we're basically what we're doing is we're using Riemann mapping theorem to change V, which is finitely many components, and all these components are simply connected. That means that V is really just a finite union of disks, right? So we can just write down a map from all of V, right? We just, on each Vj, it's defined by this map from Riemann mapping theorem. That takes V to this D. We could, and this is going to make something slightly easier. We can make Q1 be 0, right? One of these we can center at 0. And we can take we can let this C, right, this map that's coming from the Riemann mapping theorem, we can, if you remember, you can always make one point go to any point that you want. So we'll make the 0, right? That's the 0 that's in V, right? Remember, 0 was in V. It corresponded to infinity in the original setting, right? And we can make it, let's say, 0 in the first disk, right? Which we're saying is centered at 0. We're saying Q1 is 0. Now, the complement of U in the Riemann sphere is compact, right? Because the Riemann sphere is compact and the complement of U is closed. So that means, because phi is continuous, right? And this complement of U is right. Anyway, it's a compact set. Phi is continuous, so therefore it's compact, right? And it is a subset of V, right? Because V is sort of corresponds to the complement of K, right? And K is inside U, right? So the complement of U is definitely in the complement of K, right? So that's true after the inversion as well. Okay, so let's give this set after step C, right? So we take this set, over here, right? The complement of U after inversion, and we map it forward by C, and we're gonna call it S, right? And now it's a subset of D, right? And this set is compact, right? Well, again, because C is continuous, right? So continuous maps take compact sets to compact sets, right? So we have this S that is compact. Now, what does that mean? That means that we can take some R, some fixed R that is less than 1, such that S, which is a subset of this set D, so S is a compact subset of D, so therefore it's contained in some smaller disks, right? I can, still centered at the Q1 through Qn, right? But they're within some fixed small radius, right? This S is, right? So let R be that radius, right? Okay, and now we're gonna do, this is gonna be this R. That's gonna be those circles that we we're gonna go around S in the opposite direction, right? That's basically the idea. We're going around the complement of U in the opposite direction, which is gonna, after the inversion, that's gonna flip everything, and give us that we're not going around the complement of U, and we are going around K, which is now sort of corresponding to whatever's outside of these disks, right? It's not really because the map's not defined there, but in some sense, the K is, you can think of the K as whatever's outside of these disks, right? So basically, we define this gamma J, and it's the point is the key point is this minus sign, right? It goes in the opposite direction, right? You could just define it to be basically, in the chain arithmetic, right? It's the negation of the boundary of the R disk, right? So it's centered at QJ, and it goes around a circle of radius R, but in the clockwise rather than counterclockwise direction, right? And now we, our gamma is going to be, well, that's sort of, those would be our circles, but after these, two maps. So now we have to sort of pull that back to our original U, and so we're going to let gamma J, capital gamma J, be basically, we take this gamma J and we write down, we pull it back through these two maps, right? So C and Phi, right? And then gamma is the sum of these, right? Just with chain arithmetic again, right? Okay, so now, so now we have it. Now we have the gamma, and so intuitively this should work. But we have to check, does it actually work, right? So, well, let's just compute the winding numbers, right? So we start with this thing, right? That's basically the definition, right? These guys over here, these are the capital gamma sub J, right? And if we're integrating around capital gamma, it's this sum over here, right? Because we have to sum up through the gamma sub J's, right? So this is just the definition of the winding number of gamma around P, right? On some point P, but just for now assume it's just not on gamma. Now we start doing changes of variables, right? So first we get rid of we basically let you can say zeta is 1 over z, right? And you do this change of variables, and you get this integral over here, right? So, sorry, my phone rang. All right, so we get this, and it was spam too. We get this integral over here, or set of integrals. It's integral around some chain, right? And we do another change of variables. We now we pull back through the phi, and so we change from zeta to say xi, right? I mean, you could write all those as z's, but then it would be a little confusing, right? So gamma is now going in xi. So xi variable, this is happening inside the disks. Okay, so basically, this is taking the here in the first integral the complexity is in the path, right? And in the last integral, well, the path is really simple. It's just a circle, but of course I get the the complexity ends up being inside the function, right? So this is just, this is just what you would get, right? You always get from this d zeta, right? When you change, you get sort of more and more of these terms, right? Yeah. But so it seems complicated, but it's actually not that bad, right? Now it's just a nice integral around circles, right? So suppose that we have basically two things. We have to first talk about points outside of U, and then we have to talk about points in K. So let's start with a point outside of U, and let's write this function underneath the integral. Let's call it h, right, for simplicity. Now this h has two poles, and they're both simple poles. One is when this is 0, and one is when this is 0. This guy, the last term is never 0 on D, right? Because this phi prime is never 0. Psi prime is never 0. Okay, so we have two poles. To think about it, one of them for this guy that's at psi of 1 over p, and for the second term that pole is at 0 or at q1 really. Because 0 went to q1, right, which is 0, right? So we just have to compute the residues at these 2 points. It seems harder than it is, but remember, this is a simple pole. The computing residues is insanely simple, right? We have you have this as you can write this at each one of these points. You can write it as a holomorphic function divided by a holomorphic function which has a simple 0 at that point, and then to compute the residue, you just differentiate the denominator, and you plug in that point, right? That we had this proposition. I think might have been an exercise to prove. All right, so at 0, right, at q1, the residue is, well, that's exactly what it is, right? I have this bit, that's the numerator really of the, if I write the function as a holomorphic function over a holomorphic function, I can think of this as the numerator, right? Well, I can think of basically it's this bit and this bit. That's my numerator, right? With the -1, I can stick that in there, right? And we're just evaluating that at 0, right? And then we divide by the derivative of this, of c to the -1, and the way that you differentiate an inverse is inverse function terms, so it's 1 over the derivative of c at the right point, and so you get this thing, right? That's the it's 1 over that 1 over, right? Because it's in the denominator, really. And if you work this out, you can see that things just cancel out, right? You have you get 1 out of here, and this thing cancels with this thing, which jumps into the numerator, right? So I just get -1, right, coming out of here, right? Okay. Now let's look at the pole at psi of 1 over p, and that is very similar, except now I have to plug in the psi of 1 over p, and I'm also differentiating this guy, right? And my sort of numerator in this computation is this thing, right? So over here I'm plugging in psi of 1 over p, right? So that's where I'm getting this thing, and then I'm differentiating this thing and dividing, dividing by that at c of 1 over p, and so you can, that's over here, and again I just get well, now this minus 1 will cancel out this minus 1, this will cancel out this is going to be 1. So we're going to get, this is going to be p, so this is going to, or sorry, 1 over p, and I have a p here, right? So that's going to be 1, right? It's going to cancel out. So, everything cancels and we just get 1. All right. So what does that mean? That means that this winding number is 0, right? Because I get that there's two residues, and they're exactly of opposite signs, so they sum to 0. Now, really, this is these guys are going in the opposite directions, but minus 0 is 0. So, the point is that we're going around both of these. Gamma 1 goes around 0, and some gamma j, I don't know which one, but some gamma j goes around the image of 1 over p, right? 1 over p is that's the inversion, right? That's c of phi of p, right? So it's we picked R to be large enough so that it goes around S, right, which was the image of the complement of U, and therefore the winding number is 0, as I said. Okay, so that's so we have a gamma that doesn't go around U, and now let's see that it goes around K once. So suppose that we're in K. If now C was really taking the complement of K to D, right? So therefore, no C in D corresponds to P, right? Because it's precisely in that that complement, right? So therefore, H has only one pole, 0, right? Q1, right? That's the only pole that it has, right? So the other pole is just not there. The pole where we get 1 before the residue 1, right? So again, it's the same thing. Same H, where same integral. Don't have to rewrite it. We've already computed the residues. The residues are the same. It's just one of them is not inside our. One of the poles doesn't exist, right? So over here, because one of the poles is not there, the only pole is 0. Well, that was gamma 1, so it's the integral around gamma 1 of H, and now recall gamma 1 goes backwards, right? It went in the negative direction. So it's this integral is minus the residue at 0. The residue at 0 was minus 1, so minus 1 is 1, and we're done. So it's a little bit it seems a little tricky, but a lot of it is really these technicalities that made it a little harder. Other than that, it's it's just two changes of variable, which are basically that's just it's the version of calc. I mean, it is basically calc 1, right? I think it's you've seen this on some exercises, and I've actually made it and explicitly made it an exercise early in the notes, because you've done these sort of changes of variables before, right? Okay, so what do we have? We have this was this thing that seemed very reasonable, that if I had a compact set in U, I could go around in with a path that was homologous to 0 in U, right? And if you really think about it, this shouldn't really be totally trivial to see, because K can be really, really, really ugly, and U can be really ugly, right? So it's the standard proof of this, which also basically goes by by computing these sort of integrals, is to cover K by little squares, and each square has 4 sides, and we cover it so that the K is covered. You have to be a little bit careful about the topology here. So you have to, it's just also, that proof also has a bunch of technicalities. But you basically, then once you have it covered in just the right way, then you take an integral over the sides, and whenever you have 2 squares that are sitting right next to each other, then the 2 sides that are touching, they actually sort of, are not in the integral because you integrate them in opposite directions. So you can throw out all the edges that actually intersect K, right? And you would still have this, you would have this integral that's composed of sort of horizontal and vertical lines that goes around K. Again, it's sort of a simple idea, and then you have to check a bunch of technicalities. It's not really simpler. I sort of find this version of the proof that I gave. I mean, it's sort of hitting it with a bigger hammer, because we're using Riemann mapping theorem, but I find it a little bit more maybe intuitive why it works. At least to me, it seems like it. It's then it's just checking the technicalities that they all work out. Okay, so let's there was a lemma. We should have a theorem, right? So I guess the lemma is actually quite useful on its own. But let's have an application of it to simple connectedness. And it's this idea of that we've used one direction of it. So if the complement of U in the Riemann sphere is connected if and only if U is simply connected, right? So we've seen that if the complement is connected, then U is simply connected. Now, with the lemma, we can do the other direction. If it's simply connected, then we have that the complement is connected. And the way you do it is suppose that it's that the complement that the complement of U in the Riemann sphere is disconnected. So we're going to prove by contrapositive, right? Now, if it's disconnected, we can write it as a union of 2 closed sets, right? Disjoint, non-empty, and both are closed, right? Don't want to necessarily say these are the components of the complement. Maybe it has infinitely many components, but there's at least there is a disconnection, right? So So let S and K be these guys, right? S, right? They are not the same S and K as before, right? So we have two sets, right? Well, we can assume that infinity is in one of them, right? Because, well, U was a domain in C, right? So infinity is in the complement in the Riemann sphere. So we can assume that that one is that's the S that has the infinity, right? So now let U prime be U union K. That is an open set because S is closed, right? So now we have a domain, and it's also a domain in C because infinity is in S. And K is a compact subset of U prime, right? Well, because it's they're S and K are compact sets in the Riemann sphere, right? Because they're closed subsets of a compact set, right? So K is a compact subset of U prime, and we can apply the lemma. We can find a cycle that is in U prime minus K, which actually happens to be U, right? So we're basically taking, we find a cycle around K, right? So we have that it's that it goes around all the points in K, and therefore it cannot be homologous to 0 in U. I mean, it's homologous to 0 in you should mention that. I mean, it's homologous to 0 in U prime, right? But it's not homologous to 0 in U, right? Because in particular, it's K is in the complement of U, right? And so it goes around something in the complement, right? So therefore it's not simply connected. So what we proved was that if the complement of U in the Riemann sphere is not connected, then U is not simply connected. So we have both directions of this term. All right. So